Now we are going to find out how much is the energy of electron that is residing in a stationary orbit. So this is the nucleus having the positive charge, and around it an electron is revolving with velocity v at a radius r and having the mass m. So to find the total energy of an electron, revolving in the stationary orbit, is, say, E is equal to the sum of the kinetic energy of that electron plus the potential energy of that electron. So that is going to give us, we'll mention it as the total energy denoted by E of electron in the stationary orbit. Now, first we'll calculate kinetic energy. The kinetic energy of electron is given by half mv square. To calculate this, again we will take help of the same formula. The electron is revolving on the stationary orbit. So it is possessing centripetal force. The centripetal force of electron is balanced by electrostatic force of attraction, and because of this we have mv square by r. This is the centripetal force. This thing is equal to 1 upon 4 pi epsilon naught Ze into E over r square. This is the electrostatic force. So from here we have mv square is equal to 1 upon 4 pi epsilon naught Ze square over r square into r. I have rearranged. R is taken on the other hand side and this goes with one of this. So we are having the value of mv square. It is equal to 1 by 4 pi epsilon naught Ze square by r. Dividing both sides by 2, we have mv square by 2 is equal to 1 upon 8 pi epsilon naught Ze square over r. Now we'll put this value over here to find out the kinetic energy. So kinetic energy is equal to 1 upon 8 pi epsilon naught Ze square by r. So this is the amount of kinetic energy that electron is possessing while revolving around the stationary orbit. Now we can put the value of r. This is the radius that we have already found out in our previous article. The link is shared below. So I'm directly putting the value of r over here to find out the kinetic energy. Now after finding the kinetic energy, we'll proceed to find out the potential energy. Now the potential energy denoted by generally U, this thing is equal to 1 upon 4 pi epsilon naught product of the charges and distance between two of them. So we'll add the two relations for the potential energy and kinetic energy to get the total energy. So total energy E is equal to 1 upon 8 pi epsilon naught Ze square over r 1 upon 4 pi epsilon naught Ze square by r. And on solving, we'll get the value equal to minus 1 upon 8 pi epsilon naught Ze square by r. So if we see the total energy that comes out is equal to minus of 1 upon 8 pi epsilon naught Ze square by r. Or if you see the kinetic energy, it is also 1 upon 8 pi epsilon naught Ze square by r. So here we got an important conclusion that the total energy is equal to negative of the kinetic energy. Sometimes questions comes like this also, derive an expression to show that the total energy is equal to the negative of the kinetic energy. Again, what you have to do, you have to find out the total energy and the result will be giving us the conclusion. Now we have found out the total energy, and also in this expression r is the radius, and for the radius already we have derived an expression. that it is equal to n square h square epsilon naught divided by pi m z e square. N is the number of the orbital, h is the Planck's constant, epsilon naught the constant of permittivity, pi m is the mass of the electron, z is the atomic number, and e is the charge of the electron. Already I have derived this expression for the radius in my previous article, and the link is shared to find out how to find out the radius of the electron moving in the stationary orbit. Now we'll mark it as equation number 1 and this as equation number 2. Now put the value of r, that is the radius, from equation number 2 to equation number 1, and we have E is equal to minus 1 upon 8 pi epsilon naught z e square n square h square epsilon naught pi m z e square. So finally we get the total energy is equal to minus 1 upon pi cancels with pi, and we have 8 epsilon naught square h square n square, and in denominator after this we are having z square m e to the power 4. So let us separate the constant part in this expression. So this is the expression that we got for the total energy, and in this expression, if you see, z is the atomic number, m is the mass, and e is the charge on the electron, rest other thing epsilon naught h, all these are the constant values. N is the number of the orbital. So on changing this number, that is from 1, 2, 3 and so on, we'll get the corresponding energy for that corresponding orbital. Now for the nth energy state, I have taken a suffix n over here and again rewrite the expression for the energy. Now for example, the electron is in higher energy state, say n equal to 2 and energy is E2, when atom is excited. What will happen? The electron will remain for 10 power minus 8 seconds to the higher state, and then it has got a tendency to come back to the lower state. Then it comes to lower energy state, say n equal to 1, with energy E1. Then the energy difference in the two states in these two states is E2 minus E1. And for E2, n will be 2, and for E1, it will be 1. So this part is going to remain constant. Mz square e to the power 4, 8 epsilon naught square h square. I have taken minus sign common, so it will be 1 by n1 square minus 1 by n2 square. See here, this E2 minus E1 is giving us the energy difference between the two states. And according to the Bohr's postulate, he has mentioned whenever these type of transitions will take place, there will be the emission of electromagnetic wave, and the energy of that is given by h nu. This is the third postulate of Bohr's, and in the detail I have taken in the previous article, that is in the given link. So you can go through for the same. So we can find out the difference of energy E2 minus E1, and according to Bohr's third postulate, E2 minus E1, this energy difference is released in the form of electromagnetic waves equal to h nu. So according to that, h nu is equal to E2 minus E1 is equal to m z square e to the power 4 upon 8 pi epsilon naught square h square 1 by n1 square minus n2 square. Now rearranging, we have this frequency nu is equal to E2 minus E1 by h equal to m z to the power square e to the power 4 8 epsilon naught square. Now because h has been taken below that, so h square has become h cube, 1 by n1 square minus 1 by n2 square. So this is the expression for the frequency of the emitted electromagnetic waves when the electron has been shifted from the second energy state to the first energy state. Now we have calculated the frequency of the emitted electromagnetic waves. Also, we have a relation, frequency is equal to velocity into the wavelength. So frequency nu is equal to velocity, since these are electromagnetic waves, move with the velocity of light, so that is c, and wavelength say denoted by lambda. From here we have 1 upon lambda is equal to nu by c. An expression for nu we have found out. This is equal to E2 minus E1 upon c into h. And this thing will be further equal to m z to the power 2 e to the power 4 8 epsilon naught square c. Now c is more added in the expression, 1 by n1 square minus 1 upon n2 square, or 1 upon lambda. This is called the wave number. Wave number means number of waves per unit length. And if you see this mz to the power 2 e to the power 4 8 epsilon naught ch cube, all this is also constant. It is denoted by capital R, and m z square e to the power 4 8 epsilon naught square ch cube is equal to R, where R is a Rydberg constant. So these are the important conclusions that we have drawn by finding out this relation, and we will rewrite this equation for this wave number 1 upon lambda into R 1 upon n1 square minus 1 by n2 square. So finally, this is an expression for electron electrons total energy possessed in nth orbital. In nth orbital, the amount of the energy the electron is possessing is given by this expression. One more thing is here, that if we take m e to the power 4 8 epsilon naught square ch cube, all these are constant quantities. It is denoted by R. R is a constant called Rydberg constant. So if we want to rewrite again, this equation can be written as 1 upon lambda is equal to z square R 1 by n1 square minus 1 by n2 square. Now, this expression is the Bohr's formula. This is Bohr's formula for hydrogen like atoms. So what is the meaning of this word hydrogen like atoms? That are having a single electron. Hydrogen is having a single electron, or helium positive, or lithium double positive, and so on. And for hydrogen, the atomic number Z is equal to 1, using Z equal to 1 in the above equation. 1 upon lambda, this is the wave number, equal to R 1 upon n1 square by n2 square. Now the wave number for hydrogen can be found out by just having these numbers of the energy orbitals and putting these values. 1 upon lambda can be calculated. R is a constant, that is Rydberg's constant. Now here we have again taken the energy of the nth orbital, and for that expression that was equal to minus mze square to the power e to the power 4 8 epsilon naught square h square in the denominator multiplied by 1 by n square. So this is the expression that we have derived, and we have defined Rydberg constant, that is capital R, that is equal to m e to the power 4 divided by 8 epsilon naught square ch cube. And putting the values of the constant, the value of this R comes out 1.097 into 10 power 7 per meter. So this expression, on putting the value of constant R, we will be having this equation as En minus Z square R H C over N square. Now if we put the value of R, H, and C, R is 1.097 into 10 power 7, the value of Planck's constant and the velocity of light, and also taking 1 electron volt is equal to 1.6 into 10 power minus 19 joule. Now, putting the value of R, H, C and taking this value in equation number 3, we get the En, the energy of nth orbital, equal to minus Z square into 13.6 upon N square electron volt. And for hydrogen, this atomic number Z, that is equal to 1. So we will be having the energy of nth orbital is equal to minus 13.6 upon N square, and the unit will be electron volt.